Okay, so the last thing we have to do in this unit is RC circuits. R meaning resistor, C being capacitor. So there are circuits that contain resistors and capacitors. So RC circuits involve capacitors. Now, a capacitor is going to behave like a wire when it is uncharged. That is because there's going to be no resistance. There's no excess charge built up on it when you first connect it. So that means as many electrons as you want can flow on, as many as you want can flow off. Now, as it begins to build charge, those charges are going to repel new charges coming on. And it's going to become more and more difficult to get charges on there until your capacitor has the same voltage across it as is possible to supply. And once that happens, it's going to behave like an open switch. And that's because no more charges can flow onto it. So it just looks like a section where no current is flowing. So I've got a little circuit set up over here. I've got a battery supplying some electromotive force. And let's say I have a switch that's connected from here to A. I've got a resistor over here with a resistance R and a capacitor over here with a capacitance C. What I would like you guys to do is do your best to figure out what these graphs are going to look like. The charge of the capacitor over time, the current going through. Now I know it's not actually going through, but what it looks like, charges flowing in, charges flowing out. What does that current look like with C? The voltage difference across C, the current through R, and then the voltage across R. So go ahead, pause the video, take a second, try and predict those, and when we come back, we'll go over the correct answers for them. Okay, so let's take a look. Remember that the charge on a capacitor is just Q equals CV. So our capacitance times the total electromotive force on this is going to be our maximum charge. When it first starts flowing, there's no resistance to charges going on there. So we gain them really quickly. But as charges start to build up, it becomes more and more difficult to add them. And so the rate at which charge builds up asymptotically approaches this maximum amount. And it's very slow at the end. As a result of that, charges flow really fast at the start. Our current is high. At the start, it's only limited by our resistor. So current equals, since this behaves like a wire at the start, it's just going to be our electromotive force divided by resistance. That gives us our current. And then it asymptotically decreases down to zero when charges will stop flowing. Same idea with voltage. Remember, voltage and charge are directly proportional for a capacitor. So this graph and this graph are going to look very similar. With these two, since they are in series with each other, they should be identical. They should have the exact same current flowing through them. And then finally over here, these two should look opposite because I have some amount of electromotive force that's going to push electrons through this section of the through the section of the circuit. Now, as the resistance to flow gets higher and higher, there's going to be some voltage already on here. And so more and more of the total electromotive force is going to be used up crossing that capacitor. And as a result, less and less of that voltage is going to be across the resistor. So these two should be mirror images of each other, just flipped. Yeah, and that'll be what the switch looks like when it's at A. Now imagine that I allowed my capacitor to continuously charge until it's fully charged. It's the maximum amount. Current is no longer flowing. Then I disconnect the switch and I move it from A down to B. I want you guys to draw me a graph of what the charge of the capacitor is going to look like over time, the current through the capacitor is going to look like, and the voltage across the capacitor. So take a second, try those out, and in just a second we'll come back and go over the answers. All right, so let's take a look. Hey, it's pretty much how we would expect it. As soon as you let it go, charges are going to start flowing around this the opposite direction they came in to try and equalize the capacitor to neutralize it again. It's got an electromotive force on it. And so the charge is just going to be equal to, the maximum charge is just going to be equal to the electromotive force times the capacitance. Charges flow off really quickly at the start because there's an excess on one side that wants to get over to the other. As it goes, there's going to be less and less pressure pushing it until eventually there's none left when the charges have equalized. I mean, that's just going to be proportional to our current because the amount of charges flowing is our current. And then over here, these guys are going to be just off by a factor of C. But they're going to be the exact same graph. So in all of these, we're seeing that charges are flowing from the capacitor over to the other side to neutralize it through the resistor. Now we're going to go through and look at just a few more rules of how to determine RC circuits. All right, two more rules just really quickly to look at. So current flows through capacitors. It's always going to be moving through them. It doesn't actually jump the plate, but you get the idea. Until the voltage on the capacitor is equal to the electromotive force supplying it, which since we know that Q equals CV, that just means that the charge on our capacitor is always going to be equal to the capacitance times the electromotive force. So that means when we use Kirchhoff's rules for a capacitor, you're going to treat the capacitor as Q over C, which is going to give us our electromotive force for it. So you're just treating it like voltage, just like you would normally for the loop rule. Now, I've got a circuit over here where I've got an open switch, a battery, two resistors, and a capacitor. This capacitor is in parallel with that resistor. I want to know, as soon as you close the switch, what is the current through the circuit going to be? And then after I've allowed this capacitor to fully charge, I want to know, what is the current going to be? So take a second, think about those, put in your answers. We'll come back together in a second and go over it. Okay, check your answers, see how you did. For the first one, I got that the current would just be the voltage divided by resistor 1, and that's because when this guy's uncharged, there's so little resistance on this side compared to that side, none of the electrons will flow that way. Meaning we can ignore this. This is almost like a short circuit over to there. It's just gonna, this is a short circuit of this branch, meaning it's gonna skip it. So the only resistor that's limiting the flow of electrons is gonna be resistor 1, which is why current is voltage over resistance, it's just resistor 1. But in the second one, once this guy becomes charged, it's basically impassable to electrons, meaning now this is a short circuit to that. There's still resistance, so technically it's not a short circuit, but you see the idea. No electrons want to flow that way. So over here, the electrons have to flow, and since there's only one path, that means they're in series. So I just add the resistances together. Current is voltage over resistance. Resistance is the sum of them. And that's all we have for RC circuits.